Welcome back, everyone, to Chem 101. My name is Professor El Hawari, and today we'll be going over chapter number 13, which is called Sustainability and Recycling, Finding Better Ways to Use and Reuse Our Resources. We will be going over the chapter from Kimberly Waldron's 21st Century Chemistry textbook. As always, every chapter has an opener, a story opener, and our story begins on page 381 and it reads: In the distant past, telephones, like the one in the photo on the next page, had cords. These old phones weren't designed to be mobile. They weighed about 100 times more than a modern cell phone. They were clunky, yes, but they had one clear advantage over a cell phone: they were virtually indestructible. The telephone in the photo is made up of bakelite, the first purely artificial material made without any natural substances. Bakelite is a type of plastic that once was used to make everything from bracelets to telephones to chess pieces. Early plastics, uh, such as bakelite, were touted for their durability. Once a manufacturer made bakelite into a phone shape, it probably always would be phone shaped. It was incredibly tough stuff, but an indestructible product presents a tricky problem. What do you do with it when you don't want it anymore? Luckily, this was a never big concern because bakelite was not made for long, only from about the 1920s to the 1940s. Now it's a rare and valuable commodity. A phone similar to one shown here recently sold for $60 on eBay. Luckily, 21st century cell phones are not made up of bakelite. But even though our phones are not made up of indestructible plastic, discarding them is still a challenge. New phones contain toxic elements such as cadmium, Cd, lead, Pb, beryllium, Be, and mercury, Hg. The Green Beat, Chapter 3 edition, discusses the difficulties posed by the accumulation of discarded cell phones known as e waste and the effects their toxic components can have on the environment. This chapter is all about our stuff, where it comes from, how long it lasts, and what we do with it when we no longer want it. It's about how we design the materials we use to make our stuff. Are our materials extra durable, like Bakelite, or less durable and potentially reusable? What kind of trash will this material become? We'll begin in the place where it's easy to see what becomes of what we discard: the ocean. So, as the chapter tells us in the opener, telephones used to be nearly indestructible. Some weighed about 100 times more than a modern cell phone. This phone, the one that you see on the screen, is made up of bakelite, which is a type of plastic. And the problem is, it is non recyclable. It's not recyclable. And modern phones, as we said, contain many toxic elements to humans like cadmium, lead, mercury, and beryllium. Now, chapter 13 is all about stuff: where it comes from, how long it lasts, and what do we do with it when we no longer want it. The chapter begins with what is sustainability. So, as you can see, the North Pacific Gyre covers an area greater than the state of Texas, which you can see right here in the ocean. Water from all over the Pacific Ocean flows into and out of the gyre here, and you can see here in near Japan, it says trash enters the sea from land. And number two, the trash is caught by the currents. Once the trash is caught by the currents, trash carpet formed. This is where surface water contains 6 times more plastic than plankton biomass. So as you can see, the trash keeps circulating around the Pacific Ocean, and it says trash movement 6 months after entering the sea. So once it enters the sea, it takes about 6 months for it to complete this loop. And the other areas that you can see here with the dotted line is after 6 years. So as you can see, the trash is going nowhere, and it's the reason why marine life is being impacted very negatively. So the debris in the ocean collects here. 20% of the plastic made each year ends up in the ocean, which is a major problem. Now, plastic in the ocean biodegrades, which means that it breaks down into smaller and smaller pieces, which is not good for the fish or the marine life in the ocean. But this process is actually slower than on land, so plastic remains in the ocean for decades and decades, for many, many years, and it's a major problem. The fish can swallow it, so plastic in the ocean is swallowed by fish and birds and other creatures, which cause them massive problems and they eventually die. The use of plastic is unsustainable, which means that it cannot be maintained and it's a detriment to society. Sustainability, now, as a definition, that it's the capacity to endure. As an example, if we recycle 100% of our plastics, the use of plastics would then be sustainable, but we cannot. So that's why it's a problem. A life cycle assessment can help to determine the sustainability of a certain product. So as you can see in the picture here, we have the oceans, and then you can see into the factory, and then stuff lands, and then it goes into the home, and then it gets discarded in the incinerator. Now, this cycle would, you know, be sustainable, but as we know, plastic stays for a long time. Another term for life cycle assessment is called a cradle to grave analysis. So as you can see here, we extract the oil, the oil goes to the facility gets the plastic, and then it goes to another facility and eventually ends up generating electricity and some waste. So this is a cradle to grave analysis. This analysis tracks a product from raw material right here to disposable all the way to the end. A life cycle assessment accounts for all the energy and materials that go into making a product and disposing of it. So it's a way for us to visualize what is happening to the material from the beginning to the end. Life cycle analysis can be used to determine both the cost, very important, the cost of a process and the environmental impact of the process. So both the environmental impact and the cost affect the determination of the life cycle analysis. This table shows the life cycle analysis for plastic versus paper cups. So, as you can see, for plastic, the resources used in the production are natural gas, crude oil, electrical power. The price per cup is about 1 cent to manufacture. The carbon footprint is very, very high, it emits a lot of carbon dioxide, which is a major contributor of global warming. Biodegradability is very low. Contribution to water pollution is also very low. On the other hand, paper, the resources used in production are sunlight, timberland, wood, electrical power. It takes about 12 cents to make. The carbon footprint is very low, and the biodegradability is medium. The contribution to water pollution is actually very high. So, this is a way for us to figure out the differences between plastic and paper in terms of their life cycle. Cradle to cradle design includes a plan for product reuse. So, we reuse the product and then we can get it back so we can use it one more time. Products that rely on fossil fuels are not sustainable because fossil fuels are a finite resource. So, for example, coal, once it's burned off, we cannot unburn it, so it is a finite resource. Life cycle analysis can also take into account sustainability, which means that this relates to more than just raw material. It also can take into account the end of a product life. As you can see, the example that's provided in the textbook, the cradle to cradle design, Nike and Puma produce sneakers that can be recycled, which means they could be reused to make new footwear or sports surfaces. So this is the shoe right here. Now, used to make Nike grind rubber, which is used for synthetic turf, gym flooring, playground surfaces, and running tracks. So it is a way for us to be more environmentally friendly. Now, in the nature box section in our textbook, they mention landfills, paper, and the menace of single use water bottle. So they say plastic items make up only a fifth of an average landfill, and 40% of landfill volume It comes actually from paper. And as you can see here, about 40% is paper, 8% metal, 8% glass, 24% is organics, and 21% is plastic. The mass of plastic in landfill has stayed the same for about 32 years, but single-use water bottles are piling up. So as you can see, a lot more water bottles are being sold. A lot more people are using them, especially because of the water crises across the world and across the nation. And the water bottles piling up, and it's a major problem. The average American uses 167 disposable water bottles per year. The Concord, MA, became the first city, Massachusetts, to ban single use water bottles. Now, it's a way to be more environmentally conscious and to try to alleviate what is happening to our environment. Now, what is plastic, you might be wondering, and we'll also be touching on that in our lab. Plastics are polymers. So, the definition of a polymer is that it is a large organic molecule made up of smaller organic molecules called monomers. As you can see, these are all examples of polymers right here. Now, polymers can be short or long, branched or straight. Now, in terms of their structure, polymers can be stretchy, biodegradable, or have a variety of different physical properties. Now, there is also natural rubber. It is a polymer that is made from latex that comes from the Hevea brasilis tree. As you can see, there's a very large molecule, and it's a repeating unit. So as you can see, this is the molecule, and it repeats 36 times. It's a very elaborate molecule that loops around the screen. Here is the big molecule. Now, the Mayans actually harvested latex and used it for weatherproofing and to make things bouncy, as you can see in the picture right here. Now, let's talk about the physical properties of polymers. The structure of a polymer often determines its physical properties. And as we know, that structure determines function. As an example, polyisoprene contains nonpolar carbon carbon and carbon hydrogen bonds. Isoprene is a nonpolar polymer. So if you put water in it, it is not going to dissolve. The nonpolar polyisoprene polymer and polar water do not mix. Because they do not mix, we say that the polyisoprene is hydrophobic. Hydro means water, phobic means fear. Hydrophobic means a fear of water. So that's why polyisoprene makes a good waterproofing substance. So if you want to pour water onto isoprene, it is not going to dissolve it, they're not going to mix. So it's a good waterproofing substance. Polymers that are polar tend to be hydrophilic. Hydro means water, philic means love. Hydrophilic means the water loving or loves water. An example here is contact lenses. They're made from polymers that are hydrophilic. They are soluble in water but do not dissolve in water. So oxygen atoms in the monomer gives the polymer the polarity needed to dissolve in water. So as you can see, has these oxygen atoms, and oxygen makes this polymer hydrophilic, uh, which is very useful. A lot of people wear lenses. Some polymers are designed for rigidity. Rigidity means sturdy, so the structure does not break, or toughness. So instead of flexibility. So we got the picture here. This is Dr. Quillick at DuPont came up with a polymer that was rigid and packed together as crystals. She's holding the polymer that she created in the picture, like ions and solid salts. Now, the carbon nitrogen bond, which is right here, is called an amide bond, is rather inflexible. It's very tough, it's very durable, it's very rigid, and this is called an amide group. And the amide group is has two benzene rings on either sides, and a benzene ring is a six-sided ring that have the electrons delocalized in the center. Now, Kevlar is made from a rigid, inflexible polymer. And the reason why it's rigid, the reason why for its rigidity and for its inflexibility is, as we said, the carbon nitrogen bond is rather inflexible. It's very tough. The benzene rings that you can see here also adds rigidity to the polymer. In addition to that, you see a lot of hydrogen bonds are being formed between, for example, the hydrogen and the oxygen element. This hydrogen bond also adds to the stability and the rigidity of Kevlar. The polymer flexes little due to these structural aspects, making the polymer strands easy to pack closely together. Now, closely packed strands form cross links between strands, making the polymer even stronger. So you can see the polymer is stacking on top of each other. In addition to the rigidity, you have hydrogen bonding and you have the carbon nitrogen bond, and that's why this polymer is very, very strong. Now let's talk about the crystalline structure. And now a highly ordered crystalline region in a polymer is called a crystallite. As you know, crystal, the state of matter would be solid, and it's very rigid. Polyethylene, as an example, has a higher number of crystallites per volume than polymethyl cyanoacrylate, the polymer in superglue. So superglue is a less rigid polymer. It's a tough glue, but if we look at the molecular level, we would say it is a less rigid polymer. You can see polyethylene; it only has, you can think of a one. The structure is linear, but the other structure, the polymethyl cyanoacrylate, you can see has so many. It looks way more rigid. It's obviously a lot more polar. So this is what is adding to the rigidity. Now let's talk about recyclable and sustainable plastics, which is the title of our chapter. We have something called a thermoplastic polymer. Now thermoplastic polymers become more fluid and less rigid when you start heating them. Thermometer, which again is related to heat. And now they can thus be molded into various shapes as you heat them. Now, as they cool, the crystallites reform so the polymer retains its molded shape. Due to their ability to change shape if heated, thermoplastic polymers are recyclable, which means they can be used again and again. By contrast, on the other hand, thermosetting polymers do not change shape when heated and they have different properties altogether. Different thermoplastic polymers have different melting points, and differences in melting points are used to create plastics that serve different purposes. The six most common thermoplastic polymers are shown on the next slide here. So you can see PET, polyethylene terephthalate, HDPE, high density polyethylene, PVC, polyvinyl chloride, LDPE, low density polyethylene, polypropylene, polystyrene, and mixtures of these polymers. So these are the most famous of them. Now, PET is used for soft drinks, salad dressing, and peanut butter containers. HDPE is used in milk, juice, liquid detergent, and water containers, toys. PVC, that's raincoats, packaging film, shower curtains, credit cards, loose leaf binders. LDPE, bags for bread, grocery bags, zippers, seal bags, shipping envelopes. Now, polyethylene, food packaging, injection molding, automobile interior parts. Polystyrene, you got the styrofoam cups, cafeteria trays, insulation, and mixtures. You can get plastic, lumber, bottles, water, car boys and citrus juice bottles and ketchup bottles. Now, a resin ID code of 1 means the polymer is easily recycled. Now, if a resin ID code 6, it means that the polymer is less easily recycled. And if there is a resin ID of 7, it means the plastic is a mixture of different polymers. And what happens in the recycling process, it gets separated and it gets an ID, and that's how you know if something could be recycled or not. Most cities have recycling programs. Several states do not allow recyclable materials into their landfills. Some plastics in a container are used 5 times actually. Recycled plastics are used in innovative ways. Patagonia makes fleece jackets out of soda bottles. So that's another example. Also, some cities give back the money that you paid. For example, if you buy a water bottle, sometimes you also pay for the deposit. When you go and recycle this water bottle, you can get your money back. Recycled plastics are, as we said, could be used in innovative ways. Patagonia makes fleece jackets out of plastic bottles. This building in Taiwan, which is in the middle here, is built from recycled bottles. And Sherwin Williams makes paint in part from recycled bottles. So you can see the plastic in the bottle could be used in so many ways. 10% of the plastics in the US is actually recycled, and waste plastics that are not recycled end up in landfills, incinerators, or the ocean. And the problem is when it goes into the ocean, as we said, it creates a big problem. And another problem, when you incinerate plastic, it produces a ton of carbon dioxide along with certain toxic compounds that is not good for the environment. The structure of a polymer dictates its biodegradability. So polymers that degrade easily have a vulnerable spot in their structure, and that's what makes them biodegradable. Heteroatoms means these are different atoms can make a polymer vulnerable to attack by another molecule. So as you can see here, the water molecule could come. The oxygen is negatively charged, has a partial negative, and this carbonyl group has a partial positive. The oxygen can come in, attack this carbon, breaking the molecule at this point, and that's why we would say it's biodegradable. PLA, polylactic acid. But if you go to polypropylene, the carbon here is strongly attached, but these bonds can break after long exposure to sunlight. But the water will not be able to break it easily, but sunlight might do it. Polylactic acid is a plant-based polymer. It contains oxygen, a heteroatom, which makes the polymer a highly biodegradable polymer. Polylactic acid is also a sustainable polymer because it comes from fast growing plants. And now the green beat section in our textbook says the arrival of sunshine fueled batteries. Combustion of fossil fuels is a one-way street and open system. Fuel is burned, carbon dioxide is released. Need to develop alternatives, closed systems or loops. Batteries are closed loops, but yeah, and it's a big thing in the textbook. It says batteries are closed loops, but use toxic, unsustainable metals, and they wear out easily and quickly. Vengtaman Research Group developed a molecule that changes shape when exposed to sunlight. Molecule can hold solar energy until the energy is needed. And the last thing is that molecules are attached to a polymer. This polymer can hold more heat energy than about the same amount of water, and molecules can shift back and forth many, many times. And the beautiful thing is that no waste and no need to recharge. Thank you for listening to this video. Next steps, complete the quiz posted on Brightspace. Email me if you have any questions. Thank you and see you soon.